So what we're going to do now is come up with a formula for the induced EMF on a conductor. If you have a magnetic field, say into the page, right, and this conductor moves, say, to the right or the left, you'll actually get one side of this will be the positive side, one side will be the bottom. You get an induced EMF in this conductor. And this is a super cool thing, right? This means that currents are induced in conductors that are moving in magnetic fields. And there's all kinds of demonstrations. This gets really crazy with superconductors, but let's just look at the basic mathematics here. Let's derive a formula, okay? So take a look. Here's this moving conductor. Here we have these rails, these that are fixed. But keep in mind that an EMF is induced in this conductor, whether these rails are there or not. But these sort of help us derive a formula, okay? So this is going to move some distance, and sometime later it'll have moved a distance of velocity times time, right? And that new area is going to be velocity times time times L. So EMF is going to be NBA over the time it takes, right? Well, N is 1, right? So we get B. The area is going to be velocity times time times L, right? Because it moves a distance of velocity times time, and then the width of it is L, right? And then that's over the time, right? And you can see that the time cancels out. So you end up with B times velocity times the length of the conductor is the EMF induced from one end to the other end, okay? Now, you can actually derive this another way. Let's derive it. In fact, this was on an IB test. It was like, derive this, right? Okay, voltage is what? Work divided by charge, right? Work is force times distance over charge, right? So let's imagine that you've got a positive charge and that there's a force. Now remember, you could take your index finger here, right? And you can point the index finger to the right, okay? Make your middle finger go into the page, and you'll realize that there's a force on a positive charge that is up this page, okay? So the direction of the force is up the page, and it's going to do work on this charge all the way from here to here. There's this force, right? Okay, so ultimately that's force times L, which is this distance here, right? Divided by Q, right? And the force, of course, is QVB, right? From our chapter 20, right? Times L divided by Q. Oh my gosh, we ended up with B times V times L. It's crazy, right? Okay. So let's there's going to be some example problems here in a little bit. For this problem here also, right? So let's erase this, hit the right arrow. I'm hitting the right arrow. There we go. All right. So for this thing, this is our formula. This is what's in the data packet. Okay. And the direction of the where the positive charge is, we can figure this out, right? If you take your index finger, if you put a positive charge on this thing, right? So pretend there's a positive charge right here. Okay, that positive charge is moving to the right with the conductor. So you put your index finger that way. Put your middle finger in the direction of the magnetic field, in this case into the page, and your thumb is pointing up the page. So the top of this wire is going to be positive. The bottom of the wire is going to be negative by the subtraction of positive charges. Okay? Just look at these examples. These are not terribly difficult problems.